So in this example, we're going to be identifying functions. It says here, determine if the following sets of ordered pairs define a function. So here we have this set M, and it's equal to this set of ordered pairs. And let's suppose that this set of ordered pairs are the input and output values that represent a function. And we have another set here. This represents, this set of ordered pairs also represents the input and output relationship of a function. And that's exactly what a function is. When we talk about functions, we're talking about a relationship between the variables involved. One variable is the input variable, and the other variable is the output variable. So for example, if we had something like y is equal to x squared plus 1, well, we've seen that as a function, we can say that y is equal to f of x. That's our functional notation. So therefore, as a function, we can write this as f of x is equal to x squared plus 1. So if I was to make an xy table, I'll go ahead and I'll put down x here. We've done this already. And I come up with values for x, and we'll keep it simple. We'll say 0, 1, 2, -1, and -2. X is traditionally considered the input value. He's the independent value. He's the commander. He's the one who decides what's going to occur. The output value, y, but we're going to express it as functional notation, so we'll say f of x. That's the dependent variable. That's the output. So we've seen that if we input 0, so we can write this as f of 0, that's going to be equal to 0 squared plus 1. And of course, then that's equal to 1. So when we input 0, the output is 1. So what functional notation says is it's impossible to input 0 and come out with something other than 1. If we do 1, f of 1, that's going to be 1 squared plus 1. The output's going to be 2. It's impossible to input 1 and come out with something other than 2. If we input 2, 2 squared is 4 plus 1, that's 5. I cannot input 2 and come out with something like, let's just say 3. That's impossible. But students sometimes get confused, because if we do something like -1, f of -1, that's equal to -1 squared plus 1. -1 squared, that's 1, and 1 plus 1 is 2. And students see that when you slug in 1, I get 2, but when I slug in -1, I also get 2. Well, that's okay. We can slug in 2 different x's and come out with the same y, but a function says that you cannot input a value for x and come out with 2 different outputs. That's impossible. If we did -2 here, -2 squared is 4 plus 1, that's 5. So we can come out with the same y with 2 different x's, but it doesn't work the other way. So as we look at these ordered pairs up here for this set M, and this set represents the relationship between the values of a function, I'm just going to look at the x's here. I've got a 1, a -2, a 3, a 2, and a -3. So they're all different. And as long as they're all different, I guess we're okay with deciding that this does represent a function. If we look at n, and these ordered pairs here represent the relationship of a function, I've got a -4, a 3, a -3, a 3 again. So I have a 3 here for an input and a 3 here for an input. The same input value, but 2 different output values. That's impossible. I cannot input 3 for whatever this function is. I cannot input 3 and get 6 and input 3 and also get -1. That's impossible. So since that's impossible, this would not represent a function. And there we go.